screen? Can everyone see my screen? Is it visible?
Yeah.
Okay, then let's start. All right, hello everyone. My name is Dushyant. I am the Geek Chair at BITS-ACM. I'm a third year in CS. And today's orientation is going to be about what we do, what our approach to CS is, and what we actually are formally and informally, and what fields we work in. So let's begin with who we are. So formally, we're a student-run chapter, and we're associated with ACM Global, which is an organization of CS people. But you probably don't care about this because you don't even know what ACM is, right? So let's just start with an informal description. So we're a bunch of nerds. We have a mutual interest in CS, and what we're planning to do, what we ideally want to do, is to drive the way BitStreams approach CS. And of course, we're not DVM and we're not CC. We don't, unlike DVM, we don't work to make a fest work. We don't officially contribute to a fest, and we're not CC because we just do different things than what CC does, even informally. And what exactly do we do? So the core idea is to learn new tech ourselves and then to try to teach it to other BitStreams. So we hold internal activities like, let's say, internal SIGs and discussions to ensure that juniors learn to a point that they can teach others. Right? And we conduct some software-based events and expert talks during Apogee, BITS Tech Fest. That's just to stay relevant. And we run open source projects which are managed by us, by our seniors. So these projects allow the common BitStream to work on different tech in a team, like in an open source team. So it gives some exposure. We create study groups so that juniors can study topics like AI. So there are some topics that are research-based, not industry-based, like AI and theoretical CS and maybe quantum computing. So for topics like these, you don't really gain industrial skills. You read about theory, you learn theory, and then you try to apply it. So for fields like those, we form study groups so that juniors can be mentored by their seniors. We conduct some formal lectures every once in a while to teach different CS skills to BitStreams. They used to happen in the lecture halls in BITS, but since this is online SEM, we'll probably be doing it online this year. And recently, we've also introduced a summer program where we pair students with expert professors around the world for mentoring in a field. So let's say you are interested in theoretical CS, but there's no good theoretical CS facilities in BITS. There's no professor who's researching in it. So what we do is we'll pair you with some industry expert or some professor from a university abroad, and you can work under them during the summers, and they'll mentor you. They'll personally mentor you in the field so that you can progress in it. Okay, and how can you get involved? So there's multiple ways, and we're not exactly a closed body of people. So we do have core members, and the rest of the BitStreams are non-members. But generally, we don't really restrict the knowledge or the material or the resources we have. So even if you're not in ACM, you can still be a part of our activities. So first off, you can join Silica. It's a BITS Pilani CS community. It's on Slack. If you don't know what Slack is, I really recommend that you Google it. Not right now, but later. So BITS-ACM is very active on Slack, and you can engage with us there. You can ask us questions. You can ask us for suggestions on how to learn a new field, how to get into a new field. You can tell us about your project ideas. We can pair you up with seniors who are interested in the same thing. We can introduce you to new people who have the same interest so that you can learn with them and other stuff like that. It's a community. All the usual stuff that you expect from a healthy community, it's all that happens there. And like I said, we don't really reserve any special learning material or events for club members strictly. So I did mention that we have internal SIGs, which are for club members only. But if you show enough interest and enthusiasm, if you really feel that you're really into the field, if you're really excited about the field, we can let you in. It's not a problem. or like this is how you can benefit from the club's activities on campus. Other than this, you can, like, probably the reason why all of you are here, you can also be a part of the club and be at the forefront of all the stuff we do. You can you can play a role in the projects that we decide to do, in the tech that we decide to introduce to the campus, in the different let's say research fields that we decide to run our summer school in, and all of that. So you can be at the forefront, you can be a part of the process, which benefits the rest of the campus and all of that. Now, how can you join? So this is a subjective question. It's not necessarily through the test. That's for sure. I want to clarify this right here. Now, taking the test will improve your chances, yes, but failing the test doesn't mean that it's over for you. We still have members like myself who didn't do very well in the test, but got in anyway. There are other things that we look at. We especially look at how enthusiastic and eager to learn someone is. And we also look at what the current skills are. And no, these are not excuses to just take more girls. So yeah. So before we move on to the fields, I want to give you a brief overview of what we're going to talk about tonight. And first off, we're going to talk about AI. So Mantrak will tell you about the different aspects in AI, what all things you can do. Then Nandan will take up game development. Paul is going to talk about competitive programming, how you can get started, what's so good about it. Mihir is going to talk about mobile app development. Kavya is going to talk about front end. Pratham is going to talk about back end. They'll tell you what these are. No point in me describing these. Tirth is going to take up a very interesting field of CS called systems programming. And Rachit is going to talk about theoretical CS. Prarabdh is going to talk about blockchain. And then in the end, you guys are going to meet me again where I talk about computer networks. Now, we're also going to have an interactive session in the lounge after this, after the whole talk. So right now, we're just going to give you a brief overview of what these fields are, what you can do if you learn them, and what the scope is. But if you want more details about how you can start, if you want to talk to us personally, you can approach us in the lounge. We're going to be there. So with this, the introduction ends, and we can now dive in to our first field, which will be artificial intelligence. I'm going to pass the mic or stage or screen to Sumantra. Thank you.
Is my screen visible?
Yeah, I can see it.
Hi, I'm Sumantra. I'm the Machine Learning Special Interest Group Coordinator at BITS-ACM. So I'm going to be talking about artificial intelligence. And let's start what's all the hype about. So when we talk about AI, we are basically talking about decoding intelligence. And to decode intelligence, we need to first understand what intelligence is. To give you a perspective, for example, you travel from home to work every day. You follow the same route, and there is no traffic on that route. A human might be able to write a very specific set of instructions which the car or the robot can follow each and every day to get to the office. There is no intelligence involved in that. But when we bring in pedestrians, other cars, and a lot more obstacles in the course, you can talk about intelligence. Intelligence is basically the ability to adapt to any new situation. That is what intelligence is. So here is a quote by a very famous science fiction author. You can read the quote. And so since we're talking about intelligence, there are many scientists who try to formalize intelligence. One being Alan Turing himself, the father of AI. So this test is called the Turing test. There is a machine and a human talking to one another, and there is another human with his back faced, both to the machine and the human, trying to decode which one is which. If he is not able to tell or distinguish one from the other, the machine is said to have passed the Turing test. So when I talk about Turing, let's talk about a little bit about the history of AI. So AI is pretty cool today, but it was not always this way. There was a time when AI wasn't receiving enough funding. And that was the time known as the AI winter. Those were really dark times. And why, you might ask? Mainly because AI had created a lot of hype and wasn't able to live up to the expectations. What changed that? basically more computing power, more data. With all of this, we were able to go into deep learning and start using AI in real life applications. So let's talk about a little bit about real life applications of AI. So we have Google, we have Gmail, we have Snapchat. All of these are using AI, and you might not even realize it. You have a spam folder in Gmail, and it automatically sorts your mail into spam and non-spam, right? And you do not even realize that it is AI at work over here. Google is able to give you thousands and thousands of results within milliseconds, and that isn't possible without AI. The filters you use in Snapchat, that uses face recognition, again AI. You get great recommendations from Spotify and Netflix for movies to watch, for music to listen to. That's AI. But these are so commonplace that they do not amaze you anymore. So I'll try to amaze you with some applications of AI which you might not know about yet. So moving on, this is GauGAN and GANIMAL. So think about this. You make a really crude drawing, and by some sorcery, it gets converted into a photorealistic image which looks beautiful. That's exactly what GauGAN is. It is a software created by NVIDIA, and it will help you create photorealistic images from segmentation maps. So we'll get to that when you start exploring AI a bit. But for now, just it converts crude drawings into great images. Now think about its applications. People who use Photoshop usually crop a house from another image, adjust light, and a lot of other things and bring it into the current image. With this software available, you can just draw the house in your current image, and the artificial intelligence will do the task for you. GANIMAL is another toy project by NVIDIA. It will basically transfer the expression and the pose of your pet onto any animal in the world. That's what GANIMAL is. Moving on, This Person Does Not Exist is a really cool project. So this software has been able to decode what a human face looks like. And based on its knowledge, it creates photorealistic images of humans who actually do not exist in this world. You can see a GIF over here, and that's This Person Does Not Exist. And yeah, all that I mentioned over here, you can just Google it, and you will find them on the internet, and you can try them yourselves. So there is image Inpainting. Basically, a human removes the pixels from an image, and the AI tries to recreate that image using its knowledge of what our world looks like. And this has also some interesting applications. For example, in the iPad, there is a feature of removing obstructions from your images. For example, you clicked an image, but there is a net in between. Using this technique, you can remove the net from your image. So this is really, really cool. These two are my personal favorites. This is GPT-3 and AlphaGo. GPT-3 is a very recent language model. It's got 1 billion parameters, and it is like the state-of-the-art language model. So to give you an example of what GPT-3 is capable of, it is able to write poetry, which is indistinguishable from what a human writes. It is also able to write like proses about itself. I highly recommend you Google and find out what it has written about itself. It made me emotional. Then there is AlphaGo. So, okay, AlphaGo is a novel reinforcement learning algorithm, and I love reinforcement learning myself. So to just demonstrate what AlphaGo is capable of, it was able to defeat Lee Sedol, the world champion at the game of Go. And it was not just one game. The machine defeated Lee Sedol at the game in 4 games out of 5. And Lee Sedol was so frustrated by his losses that he quit Go after the match took place. And how did AlphaGo get so good? It learned from the best. It learned from itself. It plays against itself multiple times until it is the best. So AlphaGo is a really, really amazing algorithm. I highly recommend you check it out. There is a documentary on YouTube. It's 1 hour, 30 minutes long. I think you should watch that too. It's about AlphaGo. Okay. So now that I've talked about what interesting stuff is happening in AI right now, how do you get started? So AI is actually more mathematics than programming. And to get a good understanding of how AI works, what is actually possible with AI, you need to start with the basics. And nothing is better than re-implementing models from scratch. And the language of choice is obviously Python. So I highly recommend you learn Python and its libraries, NumPy, SciPy, whatever, and start re-implementing the models which already exist. And once you have a clear understanding of what is backpropagation, what neural networks are, how they work, and so on, you can actually get into the more interesting stuff, the deep learning part, where you can actually implement algorithms which have some really interesting outcomes, such as computer vision, natural language processing, and many more. Now, the internet is a boon. It has a lot to offer. But more options means more confusion. So we will obviously be providing you with a selected list of resources, which will help you out. And we will also do a little bit of hand-holding for members in our club and also people who approach us. Yeah, moving on. So these are some of the tools of the trace and some of the fields you will explore. So PyTorch is more common than TensorFlow, but yeah, and it's also performing better. So Python is obviously the language of choice, although Julia is making great advancements in the field. For computer vision, you will probably be using OpenCV. For natural language processing, you might use NLTK. For reinforcement learning, you will be using Mojoko, a physics simulator, and OpenAI Gym. So these are some of the things you'll need while working with AI. So these are a few of the fields of AI: vision, language, reinforcement learning, generative adversarial networks. So most of the examples I showed you back there were generative adversarial networks at work, and data science. Moving on. Cool things you can do after learning AI. So AI is a highly rewarding field, both in terms of pay and satisfaction. And the best part is, whatever your field of expertise be, you can mix AI with that. So for example, you are an architect and you want to design a pillar. You can use AI. There is something called generative design. Again, a really interesting field. You can Google it. You use biomimicry and AI to design a pillar, which is the most optimum pillar ever. So it has like, for example, you're a biologist. You can use AI to decode genes and whatnot. I don't know much about biology. So whatever you do in AI, it is a win-win. So you can get into research, you can think about new algorithms and so on. You can become a data scientist. You can get into teaching, you can teach other people, or you can apply AI in your field of expertise. Or if you're not much into research, you do not like thinking a lot and like implementing stuff, you can implement algorithms designed by other models designed by other AI engineers in Python. Most like researchers are not too good at programming themselves. Okay, there is infinite scope of AI, and you can read what's written on the slide, and that's all I have to say. I'll hand over this stage to Nandan, who will talk about game dev.
Hi, I'll just present my screen. Is my screen visible? Yeah. So hi, I'm Nandan. I'm the game dev team lead here at ACM, and I'm here to talk to you all about game development. So games, you can't really live your life without them. Whether you are a hardcore gamer running AAA games on your PC, or you sleep in bed and play Angry Birds, games are unavoidable basically. So game development, the name is pretty self-suggestive. You basically ideate a game, you design it, and then implement it, right? So whenever working in a team of game developers, or like even at a college level or professionally, you will most definitely follow these steps while making a game. First, actually coming up with an idea that you can implement, right? So anything that will appeal to the people. You can fix your demographics, whether you want it to be a hyper casual game for everyone, or whether you want it to be an FPS game for gamers. So after you have actually come up with your idea, you need to design your level, right? So level design is a very, very important part of game development. For example, take any FPS that you have played. Every game requires a proper map. If the covers are too much, if the map is very big, people won't like it, they won't play it. So game design is a very, very important part of the step. After you have those two things down, you actually need to go into the physics. The mechanics of a game can make or break your game, Like, so how many FIFA video clips have you seen on Instagram saying, "Oh, this is FIFA logic," right? So those bugs, they shouldn't be there. Hence, designing the mechanics of your game, actually knowing how to implement them is also very important. And then the final stage is actually coding the game, right? So that was the process. So the software we use at ECM, we mainly use Unity for various reasons. First of all, it's a free software. You can get it. You can get its pro version from for free on your BITS mail. It is very easy to develop 2D and 3D games. It is very beginner friendly, and it is also much more versatile than its other options, like as I've said in the slide, Unreal Engine. So I will touch on this versatility point a bit later, but for the modeling the game, for making the actual characters, we use Blender for complicated stuff. And if we are making simple mazes, simple stairs, anything, we either export them or we use Unity Pro Builder. By the way, the language that Unity uses for scripting is C#, which is pretty similar to Java. So if any of you are in CS, you'll get help with OOP. I don't know. So the scope. Now, let's be honest. At college level, when you are doing your undergrad degree, you don't have the compute power or the aptitude to actually make a AAA game. But if you are creative, even the shittiest ideas you have at 3 a.m., you can implement them if you know game development. Some of the hyper casual games that are popular in Unity are like Alto's Adventure, pretty relaxing game. If you want to pass time, I highly recommend you check it out. Monument Valley, that is a pretty good aesthetic game, pretty short though, and basically looking at these games, you know that they are very simple to implement, but they're very hard to think of. Hence, if you're a creative person with great ideas, game development is definitely the field for you. So the versatility point that I touched on in the initial slides, Unity as a software allows you to do many more things than game dev, right? So I have listed them here, and I will go in detail. Reinforcement learning. The new TensorFlow and Unity collaboration introduced a library called Unity ML agents. With that, you can train machine learning models to run in physical environments. For example, you want a car that is self-driving. You can train it as a model on a Unity environment. It's pretty easy to code up. In fact, one of my senior in ACM is doing Unity research in RL under a scientist. The other thing is AR VR development. So AR is a thing that can be integrated in pretty much anything, right? Snapchat has an AR feature. You can make AR games like Pokemon Go. It's the possibilities are endless. For example, just on our Pilani campus, there are two startups, Hello World and Elixir, that use AR and use Unity for AR with a extension to actually implement the startup, right? The third thing is running simulations. You can run pretty realistic simulations like car crashes to test stuff out on Unity. So those are just the possibilities that you can work with if you know how to use Unity. And last but definitely not the least, Checkmate. So Checkmate is a semesterly event conducted by BITS-ACM, where a team of you will be working with a team of game developers, a team of web developers, to basically make a game. Right? It's a puzzle-based logic game, and you'll get to work on it with yourself. This is just a snapshot of the game we made this year. We designed it all from scratch, each and everything. Usually it is done in the IPC, the computer lab at BITS, but since the semester is online, we had to make it, online. So yeah, that was all about game development. Thank you for listening. I'll pass the stage to Paul, who will talk to you about competitive coding. Thanks.
Okay, I'll be sharing my screen shortly. Is it visible? Cool. So competitive programming. What is it? It's straight up competing. I mean, you can classify competitive programming as an intellectual sport. When I say an intellectual sport, I mean a sport made for the ones with the best of minds. Because it's your job as a programmer to use every bit of knowledge you have, algorithms, data structures, and your reasoning skills to solve challenging problems in a limited time frame. These competitions are rough, they're hard, but when you get past them, it's very satisfying. The main incentive to be a good competitive coder, well, at college, well, you all came here for something, right? Many of you came for jobs. So the best competitive coders always have the best opportunities. Huge companies like Google, Facebook, they want to test your coding skills, right? If you're applying for an IT job, they're going to test you. And the way they do that is by asking questions. So a good competitive coder always has the edge over someone who's not practicing competitive coding, and they always have the better opportunities. Of course, there's a bunch of coding challenges across the world. One of them, which is really well known, is called ACM ICPC. And the top rankers in those competitions have companies straight up on their doorstep offering jobs. So you have a lot of opportunities ahead if you become a good competitive coder. There's much more benefits to competitive coding apart from just the monetary ones. Practicing code within time limits makes you a much more efficient coder. So regardless whether you wish to drop competitive coding later and pick up something that interests you, the code you make, whatever programs you write, will always be more efficient and better at what they do. You can become a faster and more focused problem solver that kind of more elaborates to the point where later down the line, you're going to be running into a bunch of problems. Your code's never going to work right in the first try. Any coder can tell you that. The thing is, and now you need to figure out what the problem is. And if you're really experienced in problem solving, you figure it out faster. You waste less time scratching your head, wondering, why is my code not working? Then there's always team competitions. And if you practice these, then you've always got your teamwork skills, which can carry forward to making large projects. If you're a good team worker, then you're going to be a good team worker now. And the last point, well, this is something which I can't really explain in this talk. It's this feeling of joy, this satisfaction you get when you solve a problem. When you're struggling at it for hours and then you finally crack it. I mean, I want everyone to like just try out one kind of competitive question after this, struggle for a while and like get the answer. In fact, in our recruitment test, the logical questions, and when you get the answers, you're going to enjoy it. There are multiple languages you can use for competitive coding, and the ones listed over here, Java, C++, and Python, are not the only ones, but they would be the advised ones, especially Java and C++, because they offer all the functionalities while not compromising on speed. Python's there. It's easy to learn for beginners because of how the syntax is. The code's readable, but to be honest, it's just not as fast. And when you're a competitive coder, you want to write the fastest program available. Even between Java and C++, C++ is more popular than Java. There's minor differences, such as the writing the code. C++ has shorter, simpler syntax, so it makes it more readable while being faster to write. And the program is also slightly faster. There's a bunch of platforms you can use for competitive coding and to brush up on your skills. Codeforces being one of the most popular. Codeforces has weekly contests, sometimes contests twice a week. So regularly practicing on that and increasing your rank is one of the best ways to become a good competitive coder. There's many others, such as LeetCode, which offer questions more oriented towards interviews. HackerRank has one of the best bases of problem sets, and one of my favorites, really. Plus, the interface is really nice. And they've listed out their problems with a great difficulty order, too. CodeChef is for those who don't want that whole time limit stress factor behind their competitions. And they offer much more relaxed competitions with the much larger time frames. so you can leisurely code and think about your solutions. One thing competitive coders do need is a decent amount of mathematics skills. You'll reach a point where your coding is limited by your knowledge in maths, and Project Euler is a place where you can test out your mathematical skills because they offer a large selection of problems of increasing difficulty, and they don't really ask for a limited time frame. But if you don't solve the question efficiently enough, your code actually might take a couple of years to compile. So why competitive coding? Why efficient algorithms when everything's becoming more powerful? And the fact is, you always do need more efficient algorithms. You need to write code the best way possible. At least that's something I believe. You should have clean code. For example, the computer that sent NASA to the moon, sent man to the moon, it had 4 kilobytes of RAM, 32 kilobytes of storage. You have to understand the efficiency of the algorithms that were coded for them. And it's some of the magical things you can do if you're a competitive coder, but you need to be one of the best. Anyways, moving on from competitive coding would be mobile app development. I'll give it to Mihir.
Yeah. So can you see my screen?
Yeah, we can see it. You can continue.
Okay, so what is mobile app development? The answer to this question is actually really obvious, It's the process of developing mobile apps. And you know how important mobile apps have become in our recent times. So in any way you want to use your phone, you would actually be interacting through mobile apps only, right? So it's actually really important for our phones or actually our personal lives. This statement we have here is from Raj Agarwal, who is the CEO and founder of Localytics. And it very well states the fact how the people's expectation from even websites have started becoming more app-like. So app development has actually become really important for both business development as well as for people freelancing it. So I'm presenting here some cool facts about mobile apps. In 2019, we had about 204 billion app downloads, and that was actually excluding reinstall and app updates. By the month of August 2020, Android app users had a choice of about 2.7 million apps from Google Play Store, while Apple App Store users had a choice of about 1.82 million available apps. And India's mobile phone industry is actually going through a great boom, as in you are going to see that the expectation for the mobile application designers by 2021 would be around 200 million. Now let's talk about what are the mobile development tools. These tools are actually the tools which are used for constructing the mobile apps, and these are actually categorized into 2 categories. These categories are native mobile development tools and cross-platform mobile development tools. Let's see what these 2 development tools are. Native mobile development tools, they are used to create specialized apps for a platform, and they can actually take a good advantage of the features which are present on that platform. So for example, Android Studio can very well make use of the abilities of the Android OS, while Xcode can make use of the abilities of the iOS. Android Studio is actually programmed using Java and Kotlin. These are just programming languages. You can learn about them more later. And these apps actually made some really famous apps, like the Android versions of Uber and Coursera app. And then we have Xcode, which is programmed using the Swift programming language. And some famous examples are the iOS versions of LinkedIn and Facebook app. Now we talk about cross-platform mobile development tools. These are actually used to make some really generic apps that can run across multiple multiple OS. And that means that you can run the same app using Android OS, tvOS, or iOS, and you don't have to write really separate codes from them. But one disadvantage they face is that being really generic, so they can't make use of the app platform specific features. So it's really a trade-off between quality and cost. And some examples are Flutter and React Native. Flutter can be used for making Android OS, desktop, or iOS apps. And the apps are programmed using the Dart language. And some popular examples of Flutter are Google Pay and Google Ads. Then we have React Native, which can be used for programming apps for web, Windows, iOS, tvOS, etc. And these are programmed using JavaScript and React. So now I would be handing the mic to Kavya, and she would be speaking about front-end development.
Hello, am I audible?
Yeah.
So today I'll be talking about front-end development. So so first we'll start about what is front-end development. So a front-end of a software or a website is everything that the user will be interacting with. Now, from a user point of view, front-end is basically the user interface of the website or the software programming that the user is seeing. But as a developer, you would be actually building and programming those user interfaces. Now, one of the primary goals of a front-end developer is to create a smooth or a frictionless user experience, which is also known as the UX. Now, the UX should be really intuitive and easy to use. And now think of an example of a site like google.com. You can access through your mobile phone, to your tablets, through your laptop, and you definitely feel the same user experience throughout these devices. And that's why the modern web development should typically involve responsive design. Next slide. Now coming to front-end frameworks and languages, we would be talking about the three languages, which are HTML, CSS, and JavaScript. HTML is for added meaning to raw content by marking it up. Then CSS is for formatting that marked up content, and JavaScript is for making that content and formatting interactive. Now think of HTML as the abstract text and the images behind a web page. CSS is the page that actually gets displayed, and JavaScript is the behavior that can manipulate both HTML and CSS. Now I'll talk about the JavaScript frameworks, which are React, Angular, and Vue.js. React is developed by Facebook, Angular is developed by Google, and Vue.js is an open source community project. Next slide. Also, React is a highly dynamic framework, and it offers great support in creating interactive user interfaces. Now, companies like WhatsApp, Instagram, PayPal, Glassdoor, they all use React. Vue.js is a relatively new front-end framework that it has gained popularity recently, and it's highly in use now. And then there is Angular also, which is developed by Google. Now you all must be wondering that why am I talking about these JavaScript frameworks for development? Why can't we just build frameworks build front end using the normal HTML, CSS, and JavaScript? So JavaScript is basically the dominant client-side scripting language of the web, and most of the websites are using JavaScript for their front end. And the JavaScript frameworks have those functions which the programmers can manipulate and use them for their convenience. Now, frameworks are more adaptable. They help you to save time, and therefore they are more widely used for developing the front end of websites and software programs. Next slide. Now, coming to the scope of front-end development, the career outlook for front-end developers is excellent. There are various number of job openings for front-end engineers and interns. While in college, you can grab internships with this skill at companies like Spotify, Twitter, Google, Postman, and many more. You can also contribute to open source programs such as Google Summer of Code, GSOC, JavaScript Summer of Code, JSOC, and Outreachy, and so on. Now I'll hand over to Pratham for backend development.
Hello, I am Pratham, and I'll talk about backend development. So, what is backend development? Backend is the code that runs on the server. Backend is the code that runs on the server and makes the website dynamic. So, what do I mean by dynamic? If you open Facebook, no two people usually have the same content on their feed. It is personalized to everyone. That is the job of the backend. So it contains all the website's core logic, and the front end contains stuff which is related to the user experience and the interface, whereas backend is related to the actual logic which makes it possible. So some of the examples where we use it is storing data. Like everyone of us has used Google Drive. So we are storing all our files on the Google Drive backend. Similarly, when you upload a photograph to Instagram, so it has to store the photograph, the video with all its comments and likes, etc. The second example could be authentication. Facebook has to make sure that no one can message someone without logging in, so that there's an identity to every person. And the backend decides what is the data which has to be shown to the users. Like if you are searching for something on Google, the search algorithm will show you the results. So why do we use it? For safety, first of all. Backend is a critical logic without which the service can stop working. You do not want to give a lot of access to the client. So it is way more secure to run it on a computer that we can physically maintain and protect. Imagine if Facebook's authentication was on my own computer, then maybe a hacker could just get access to my system and then gain access to people's accounts. Second is performance. If we search something like dog humps a broomstick, then Google will return 120,000 results in half a second. That is a lot of data, and we cannot search so quickly on our own laptops, even if we run Google's software on it. So the backend, it is a backend job to provide these, the algorithm on that high performance server. Accessibility. Our mobile phones and our computers do not actually contain the code which Google uses to give us the results. And with a good backend, Google has ensured that we can use its services from any device without downloading any software. We just have to tell the server what we want, and it sends back the results. So how do we make this possible? There are a lot of frameworks for backend. A framework basically makes our life easier so that we do not have to make stuff from the ground up. The most popular one is Django, which is written in Python. It is very popular in the campus. It is easy to learn. You can get a project like started in a day with it. You do not have to mess around with stuff, just setting it up. It is used by Instagram and YouTube. The second framework which has really picked up on campus, and there have been a lot of projects made last year using this, is Node.js using this Express framework. It is a little harder to learn than Django, but it will give you a deeper understanding of how the web actually works. It is used by Uber, Netflix, PayPal. It is really easy to make chat applications like anything real time, chat, games, real-time communication. Third is PHP. No one here uses it now. It is outdated, so don't use it. And last but not the least, we have Go, which is picking up on campus. Right now, it is moderately difficult to pick up, but it has a lot of advantages like a very rich standard library and high concurrency. So you have to choose your framework, whichever you would like. We would suggest you to start with Node. Thank you. Now, these will be telling you about systems programming.
Pratham, can you stop sharing? Yeah. Give me a second, I'll share my screen. Yeah, is this visible to you all? Yeah, so I'll be talking about systems programming. So firstly, I tried to find a definition for systems programming, but it's kind of an umbrella term. So let's begin with an analogy. Let's say you're someone who's making an aeroplane. So you'll need thrusters. So let's suppose there's a company that's making the thrusters for you. So your job as an airplane maker is to assemble the thruster and make sure it works well with the rest of your aeroplane. This is what application development is, but the job of developing the thruster itself, so that other people can use it to make their own aeroplanes, is basically systems programming. Systems programming is programming at a lower level. You'll work closer to the machine. You'll be directly accessing the memory. It's basically the infrastructure that is used to facilitate software. So what does this mean? Okay, so let's say you're like Nandan, you're a game developer. You won't be building your own engines to every time you have to make a game. You'll be using something like Unity. So Unity is a software system, or Unreal Engine is a software system that facilitates the development and the running of video games, so that everyone doesn't have to make their own engine every time they have to make a video game. Applications of systems programming. So the very first thing that comes to your mind when you hear system is an operating system. The operating system is the most fundamental system you can have. You have a machine, you want to run programs on it. So you can't directly run programs on it. You need to facilitate the communication between your machine and your programs. So the operating system does that. It lets you run whatever you want on your computer. So other people can directly write software without having to take into account the intricacies of every laptop or every PC that's into existence. Another thing is device drivers. So consider this: when you connect your keyboard to your computer, it magically knows that it is a keyboard and not a mouse. And when you press spacebar, it knows that it is a spacebar. How does that happen? There's a piece of software called a driver that tells your computer that, okay, this piece of hardware is a keyboard, and when I send this signal, or when this key is pressed, this is a spacebar or this is a backspace. Next is databases. So the world currently runs on a lot of data. Companies like Facebook or WhatsApp or Instagram have to store a fuck ton of data. How do they store this efficiently so that they're not wasting space? How do they store this reliably so that it's always available? And how do they store this such that no one can enter with bad intentions? This is all part of database design. Databases are actually quite complex systems. So next is 3D rendering. We already talked about Unity. Stuff like Unity or Blender or Unreal Engine, these things make it possible for you to write pieces of code and they magically turn it into graphics. So you don't have to do it yourself as a game developer. You don't have to think about converting that code into graphics. You just have to write the code. Okay, so draw a square here, and the game engine or the 3D renderer will magically draw a square or a cube there. Media codecs. So, everything is stored as a series of ones and zeros on a computer. It's basically data. So when you have an image file, how does your computer know that, okay, this image file is supposed to draw this picture of a tree here? How does that happen? You have set protocols, or you have a set of rules that tell the computer, okay, this piece of data will convert into this color or this pixel here at this position. And your photo viewer or your video player or your music streamer can then render it accordingly. So systems, so as you can see, systems programming is about a lot of things, but it's basically about developing software that works on a lower level than end user applications. So you're facilitating other software engineers to be able to make programs for end users or the gen population who don't understand code. So let's say I'm developing my own system. I'm writing a piece of software. I have a magical idea. Now I start to think about its implementation. What all should a good system software characterize? What all should it have? The very first thing is robustness. Well, this can be said about a lot of software in general, where software should be robust. Things will not always go according to plan. So when things inevitably do fuck up, how do you handle those fuck ups? Next is safety. You only let the user access as much data as it is required. The rest of it, you hide it from them. It is you don't let bad guys enter because that's always a problem. You don't want people messing with your system. So how do you manage these things? That's what system software is about. Next is fault tolerance. Let's say you're uploading a video to YouTube and your internet dies midway. So what happens with the bad data? Like you uploaded 50% of your video, and the rest of the 50% wasn't able to upload. So what do you do with the 50%? Do you accept the 50% and continue, or do you tell the user that okay, this is only half of the video, I'll need the rest of it, or do you like delete the whole video? Like these are choices you'll have to make as a systems programmer. Fault tolerance is basically recovering from a fuck up. So it is upon you to decide what characterizes as a fuck up and how do you recover from it. Extensibility. Okay, so most of us are using AdBlock. Okay, so you might have thought, okay, AdBlock is such a nice feature. Why isn't it shipped as part of Google Chrome itself? Why is it? Why do I have to download it? That's because Google Chrome ships with only what is very essential for you to be able to go to the internet. Whatever else you want can be added as a plugin or an extension on Google Chrome. This is actually a good rule of developing software. Only give people what they need, and the rest they can develop themselves, or the community can develop for them. So now, if I wanted to write AdBlock, I don't have to actually mess with Google Chrome's code. I don't have to hack at Google Chrome ka code base. Google Chrome exposes a set of rules. Okay, do this, and you'll be able to block ads. That is extensibility. Good system software is always extensible. Common challenges. So yeah, so making my piece of system software, what kind of challenges will I encounter? First of all, unlike other programming, unlike stuff like front-end or back-end development, you'll probably be dealing with bytes of data. A byte is basically a series of zeros and ones. You'll need to manage your own memory. So your program cannot be using. So Google Chrome is notorious for using a lot of RAM. So a good system software uses a minimum amount of memory. So you don't need more than you essentially have to. Minimizing overhead. So what is overhead? Overhead is basically, so let's say I have to add 10 numbers. Let's say I have 1 to 10 and I have to add all of these. Anything I do except from adding 1 to 10, every variable I declare, every space I allocate is overhead. Everything I'm doing other than adding these numbers is classified as overhead. So system software needs to be fast. It needs to have minimum memory usage. So you have to be minimizing your overhead. You need to do things as efficiently as possible. Things have to be fast. So Paul talked about algorithms. So a lot of these times in competitive coding or like writing software in general, you'll be using algorithms that work serially. What that means is you'll be writing algorithms that perform one thing after the other. But as you know, the modern computer, we're not making our processors faster. We're adding cores to our processor so that they can't do one thing faster, but they can do multiple things at once. So to be able to efficiently make use of the modern computer, you have to write multi-threaded or parallel algorithms. Parallel algorithms are basically algorithms that do multiple things at once. So yeah, I thought about the design. I thought about the characteristics. I know what the common challenges are. What will I use to write my first piece of system software? The most popular language is C or C++. It has been in existence for the longest. It is very popular. It is almost everywhere. But The problem with C and C++ is it is riddled with bugs. Software written in C++ requires a lot of experience. You'll need a lot of experience to write anything using C++. It's so unlike Python. So if you're starting with Python, or you start learning Python today, tomorrow you're able to write a piece of software. But those of you who worked with C++ know that it's not the case with C++. You have to spend a lot of time to be able to write anything meaningful with C++. Java. So Java is an enterprise favorite. That is probably because Oracle has made it to be that way. The entire Java ecosystem is directed towards enterprises. So it is very popular among like stuff like banks or big companies that need to have software that's reliable and scalable. Two new competitors here are Golang and Rust. So Golang is a relatively new language. It came out, I think, 6 to 7 years ago. It is very C-like. So programmers who are already used to C don't have to learn a lot. It feels very C-like. And concurrency in Go. So concurrency is basically parallel programming. So doing multiple things at once. So concurrency in Go is very easy. It's very it's nice to use. Basically, it's fun for you. So yeah, Rust. Rust is a pretty strong competitor to Golang. Rust is even newer than Golang. It operates at the level of C++. So whatever you can do in C++, you can do with Rust. But Rust is much more safer. It virtually eliminates a lot of bugs that C++ had. So if any of you have ever encountered a seg fault while working with C++, know that Rust does not allow you to have a seg fault, like ever. Rust is designed in such a manner that you can never encounter a seg fault. So yeah, that was about the languages we're using. But let's talk about why would you want to write system software? I mean, you could rather be writing backend apps, or you could rather be writing frontend for your new startup. So system software is software that enables developers to write end user software. So let's get real. Making web pages is cool. Training your neural network to be able to make people out of nowhere is cool. But what facilitates these things? The engines, the runtimes, these things are possible because people have written very efficient engines, very efficient runtimes, so that things can be very fast for these people. As Sumantrak was mentioning, AI didn't receive a lot of praise in the beginning because it was very inefficient. But with the development of new software or new systems, AI has picked up a lot of pace, and that is possible only because systems programmers are working their asses off trying to make things more efficient day by day. Let's talk about YouTube. So I am a creator. I upload a video on YouTube. It's probably, so I have a DSLR cam. It's probably a 4 gigabit file. I upload the whole video on YouTube, and now people want to watch that video. So I can't directly be streaming that piece of video to everyone. There's a lot of things that need to happen with the video to be able to stream it to millions of people, and that too without interruption, very smoothly. A few things that need to be done are converting the video, making it smaller in size, being able to stream it to thousands of millions of users concurrently. So these things are part of the systems that YouTube is running behind the scenes, the stuff you don't get to see. So yeah, why should you be doing systems programming? So one very simple reason is you really like programming. So ML and AI is cool, but as Sumantrak mentioned, it's more math than programming. So if you have the knack for programming, if making things fast or making good software gives you satisfaction, systems programming is definitely for you. If you like making design choices, so a lot of systems programming is about making choices. it's about doing things a particular way, and there's a lot of disturbance in the background. Can you mute yourself, Pratham? Yeah. So yeah, you should be doing systems if you like making design choices. Design choices like why should you do a said thing a particular way? Like if you're uploading videos, when should they be processed, or what amount of processing should they receive? Stuff like that. Yeah. Another very good reason is you started with software development. You got bored of it because developing end user software is good, but it gets pretty redundant pretty quickly. So that's another good reason. So yeah, that's all from my side. Rachit will be talking about theoretical CS next. So I'll hand it over to him.
Yeah, can you, right. Is it visible? Are the slides visible?
Yeah.
Cool. Right. So theoretical computer science is a natural bridge between mathematics and computer science, right? And both fields have benefited a lot from this connection. This field is basically the backbone of the tech that you're using. It all comes down to this. So the algorithms that engineers use are designed by theoretical CS researchers, right? Let's see what all there is in this field, right? Cool. So one of the most well-studied field in theory is algorithms. And now you'll probably do these for competitive as well. Like algorithms, they're used everywhere. So what are algorithms? So it's basically a set of well-defined rules, a recipe in effect, for solving some computational problem. Maybe you have a bunch of numbers and you want to rearrange them so that they're in a sorted order. Or maybe you have a robot and you want it to travel from one point to another, taking the shortest path. Programming language theory basically tells you how to write a programming language that is good and that works. Now, so there is a lot of like rules that you need to set down for a language to work. There have to be you need to make it efficient. You need to make it secure and stuff like that. So programming language theory deals with that. Let's see. Yeah. Oh, quantum computing sounds shiny, right? So, well, it is. Like quantum computing is the future. We don't have a functioning computer yet, but people have already started developing algorithms for this computer. You heard Sumantrak talking about AI, right? Well, AI is actually pretty slow. Like it takes a long time for models to train right now. And I'll give you an example. So IBM's Deep Blue computer defeated Garry Kasparov. He was a chess champion because it could calculate 200 million potential moves every second. With a quantum computer, these calculations could be 1 trillion per second, right? Game theory is a fun field full of real-world puzzles that we solve by developing strategies and developing decision-making algorithms. These seemingly small puzzles have applications in huge fields like economics, trading, finance. So algorithmic trading is basically based on game theory, right? Apart from this, we have cryptography. Cryptography is the study of algorithms to protect and encrypt data. Now, this is an extremely relevant field right now because we have a lot of data that needs to be protected. And it has a lot of interesting research happening all around the world. I mean, it's an amazing field. So let's talk about how you can get into theoretical. So first of all, don't be intimidated by the topic names. Last slide was full of big names, but I can assure you that like seniors on campus and in ACM are doing these topics. They're pursuing these things. So it's totally possible. The best way to go about this is to learn some basic theory from standard books and try to get a project under a prof, because a prof has experience and you'll need that experience to not get lost and basically navigate through theory. So once you have some basic knowledge, you need to explore the field through research papers. It's important that you read these papers, because this opens your mind to new ideas. And a lot of the state of the art research, it's not there in books. I mean, so at some point you will have to start reading papers. Don't worry, you don't have to understand everything in the paper. You just need to get a basic idea of what it's talking about and what the final result is, like what the paper is actually doing. So it's important that you have a study group or a community to discuss ideas and doubts. Silica solves that problem. It's the campus CS Slack group with over 600 members. I would also suggest that you, like, while learning, you write about the stuff you learn. It helps you see how much you've grown. So if you ever want to write about anything cool you've done / learned, you can do that through ACM's blog. You don't have to be a part of ACM to write for the blog. It's possible for each and every one of you. Cool. Let's talk about what kind of things you can do through theoretical CS. So you can work in like a big shot company as a researcher. Almost all big companies have an R&D team that does theory. I mean, IBM quantum research is just amazing. Like, so Google also has an algo and combinatorics team that works there. So yeah, you can also do research in private labs like Max Planck, Germany, INRI, France. And so there are a lot of private labs that are funded from the government and from other sources. And they do great research. Like you'll get to meet amazing people. You'll get to work with awesome minds. Or you can join academia, become a prof, and do research, innovate in fields you're passionate about. So research is pretty rewarding. I mean, you get to do what you like, meet new people, meet interesting people innovating in your field, and you get to travel around the world presenting your research at conferences. So theoretical CS is an amazingly fun field. You work with the fundamentals that drive technology around the world. You prove results that have an impact in so many interdisciplinary fields at once. Like, for example, computational biology uses dynamic programming algorithms to measure genome similarity. I mean, how like bio and CS coming together. So a lot of these fields do come together, and yeah, it's an amazing feeling to contribute at such a fundamental level. I'll now give the stage to Prarabdh. He'll tell you about blockchain.
Good evening, everyone. So, like you all must have heard about cryptocurrencies like blockchain, like Bitcoin, and so one of the one of the most core technologies that allows cryptocurrencies like Bitcoin to exist is blockchain. However, at this point, I would like to make it clear to everyone that blockchain is not Bitcoin, or it is not only limited to cryptocurrencies. It has pretty more uses apart from cryptocurrencies. So let's deep dive into some of them. So what is blockchain? As the name suggests, blockchain is simply a chain of blocks. Uh, in a more formal sense, blockchain is a distributed immutable ledger. For people who don't know what a ledger is can simply be seen as a notebook where people record transactions between each other. It could also be visualized as a passbook for your bank account. The another important thing is it is immutable, which means that once a transaction is recorded in the ledger, the transaction cannot be rewritten or changed. The details of the transaction cannot be changed. This is a pretty important property for many applications. Also, it is distributed. That means that the data is not stored at one computer, or like one entity does not has the entire control over the data, which makes it more transparent and more accessible. So block data that is to be written in blockchains is grouped into blocks. These blocks are cryptographically linked together in order to make the chain immutable, and separate entities have separate copies of the ledger to make the process transparent and make it distributed. So what makes blockchain so powerful? So the most important thing is that there is no central authority which has control over it. So this allows a lot of transparency, but it can at the same time it also allows anonymity to its users. That is, you cannot identify a specific user and its activities on the blockchain, which is pretty important in financial circles as well as other areas where blockchain is utilized. Apart from that, the immutability of the chain makes it ideal to act as an archive of things that won't be reversed or that won't be changed in the future. Recently, a new concept of smart contracts is also coming up, which basically you can visualize it as you upload a program on the blockchain, and the program then runs in a distributed manner indefinitely. So, like, you can do some pretty amazing stuff with such programs. Like, we'll talk about one at the end of the presentation. So after learning blockchain, like why would you learn blockchain, and what could you do once you have learned blockchain? So you could become a blockchain developer. That is, you would be developing those smart contracts which I was talking about using Solidity, and like these smart contracts would basically help you develop real world applications using blockchain. If you want to go towards the research side, you could research on integrating blockchain with other domains of computer science like IoT, or even outside computer science like finance. Uh, or you could research on distributed algorithms, like algorithms for developing consensus or algorithms for fault tolerance. You could also get into the field of research of security of blockchains, which is also a very promising field of research in blockchain. Now, let me talk about one of the proposed applications of blockchain, which makes the technology pretty exciting for me personally. So, I'm going to talk about distributed autonomous organizations. They are known as DAOs, and they are basically smart contracts, a large number of them, which are interconnected in their functioning. And so, what we could do with this group of smart contracts is we could make an organization that runs itself. It would this organization would be completely human free, and it would need no support from humans to run itself. This organization could also be made ownerless, that is, no single entity or even a group of entities, nor a group of entities would be owning it. It would be in the public domain, similar to open source codes. So let's have a look at the example to see how DAOs look, and how they could be made a possibility. So imagine a DAO similar to Uber that provides taxi services to people. So for example, this person needs to go from home A to home B, point A to point B, and he wants a ride. So and imagine a taxi which is self-driving, like there is no driver involved, and this taxi and there is a smart contract on the blockchain which determines which basically has an algorithm allowing the taxi to find its nearest customer. Once that is done, the customer takes the ride, reaches point B, and then another smart contract allows the customer to pay to the organization the amount due Now imagine another scenario when the vehicle detects that its fuel is getting low and it needs to refuel at a petrol pump. Now, after refueling it, a smart contract in the petrol pump will enable the transaction of money between the organization and the petrol pump, and this process would be completely human free. We could also lay out rules to, for example, increase the number of taxis in this organization or reduce them based on certain constraints, and so the organization would be able to expand and contract as well without any human interference. So this was one use case which actually draws me towards blockchain. There are many others, and I would be happy to discuss them in the launch session after the orientation. Now I would like to give the mic to Dushyant to talk about computer networks. Thank you.
Is my screen visible?
Yep.
Okay, I'll start. The slides are way down, apologies. Okay, can you guys see the slide? I'm assuming that you can. So let's start. So first of all, computer networks have been around for what? For more than 30 years, right? It's an old concept. And the fact that it's old makes us question, like, what's so good about it? I mean, if something is this old, like imagine cars, there's no revolutionary innovations in the field of cars, right? Because they've been around forever. So same with computer networks. We've had them since like 1980s, even before that, and now they're really mature. Our networks are strong, they're fast. So why am I talking about this? Okay, so you've heard of buzzwords. Most of this orientation has been about buzzwords. It has been about buzzwords to attract you guys here so that we can pitch ACM to you. Now, why is computer networks a buzzword? So you've heard about 5G, right? There's like it's been in conversations lately. The new iPhone. If you've heard about the new iPhone, the variant in USA, it's coming with 5G, which is part of the hype, right? So what's so great about 5G? Well, it's faster than 4G, which is pretty much all that we care about in a network. And 5G is a networking concept. So when I talk about computer networks, I don't just mean the usual Ethernet cables and stuff. I mean making actual devices talk. So when you are calling someone when you dial to someone, not a WhatsApp call, when you dial to someone, it's still happening over a network, and that's still a computer network, and that's what we're talking about. So let's go back to like 2013, 2012, and if you remember back then we had 3G, 4G and stuff, and a speed of 2 megabytes per second was like a big deal. You had to pay a lot for it, like before Geo came and everything. And yet now I'm currently giving this presentation over a connection of 30 megabytes per second from Airtel. So what changed? Because information will still travel at the same speed physically. Like if you use optic cables, it still travels at the speed of light, right? You can't beat that speed. It doesn't get any faster than that. So what actually did get faster? So the answer to that is nothing. We just designed the networks in a better, more robust way. And to be more precise, we rebuilt our networks to be programmable. And it gave birth to a new field, which is called software-defined networking. Now, what are programmable networks? So imagine some jerk parks their car in the middle of the road and there's a traffic jam. So what do you do about it? Like generally what you'd need to do is to get the guy to remove his car from there so that the traffic can continue. To take the road from before the car and join it to something else, like just pick it up and join it to something else. If that was possible, we'd get much better traffic management, right? So that's kind of what the people who started SDN thought. So what does being programmable mean in general even? Like what does it mean for a computer to be programmable? It basically means, what?
Your screen share stop.
Oh,
The screen's not visible right now.
okay.
Yep.
I'll just do it again. Can you see it now?
Yeah.
Yeah, I mean, I'm just using the
Yes.
slides as cues
Yeah.
anyway. You don't really, need the slides to understand what I'm saying. But okay, let's move on. So what does being programmable mean? What makes a computer programmable? What does it fundamentally mean? It means that you can specify how a computer will behave in different situations. So like, let's say you have a program that's supposed to calculate the square of a number. So if you give it an input of 1, it's gonna output 1. If you give it an input of 3, it's gonna output 9. So it's giving different outputs for different inputs. So it's behaving differently in different situations, right? So that's kind of what we mean by programmability. We should be able to specify to the computer what it should do, like how it should react to different inputs. And we can take the same idea and apply it to networks as a whole. So what does a programmable network mean? It means we have a network that will change itself, change its structure, change the way it's operating based on what kind of traffic it's getting. For example, like if a particular network node is like under too much traffic, the network would change its structure to redirect some of the traffic to other nodes to ease out the burden. So like, you remember the staircases from Hogwarts, right? You just go down a staircase and the staircases rearrange themselves, floating through the air to get you to the correct destination in the least amount of time. So that's kind of what we're trying to do here. So like it's pretty novel, and some parts of it, like let's say data plane programmability, those fields have been around for less than a decade, and they're pretty new. There's a ton of research going on, and that's why changing the structure can, it can improve speed. So I'll give you another example. Let's say you have to send a message from point A to point B, but if you lose even a single bit of information in that message, you have to send it again. So what happens if you lose the bit? You'll have to send it all over again, and the round trip time will now be 2 times the time that you'd originally need, right? So if by improving the network structure, you can eliminate that error, then you'll have a round trip time that is now the original time, which is half of what is usually required, right? So that's how changing the structure of a network, making it more robust, making it programmable, actually allows us to deliver data in a faster way, even though we're limited physically by the speed of light. So that's our programmable networks. And with that, we'll be concluding. So yeah, obligatory thank you slide. Now I'm gonna take questions.